Hi everyone, welcome to our lesson on graphing polynomials using a table of values and taking a look at end behavior. So by the end of this worksheet and this lesson, you should be able to determine the leading coefficient and the degree of a polynomial, understand what standard form is, and graph a polynomial function using a table of values and end behavior. You should also be able to describe end behavior of any polynomial function. So let's recall some information. A monomial is a number, a variable, or the product of a number and one or more variables with whole number exponents. A polynomial is a monomial or a sum of monomials. A polynomial function is a function of the form f of x equals an times x to the power of n plus an minus 1 times x to the power of n minus 1, and so on and so forth until you finally get to the constant term, which is a naught. So an an is not equal 0. So the exponents are all whole numbers and the coefficients are all real numbers. And for this function, an is the leading coefficient, n is the degree, and a naught is the constant term. A polynomial function is in standard form when its terms are written in descending order of exponents from left to right. So here we go with the table. Shows some polynomial functions that you may be familiar with. So remember the degree. The degree is the highest exponent, and then that'll give you the type of function, and then we'll write out the standard form, and then we have an example. So for a degree of 0, that means we have a constant, and the function is f of x equals a naught. So that would be a constant number. So for example, f of x equals negative 14. Next, if we have a linear degree, that means we have a degree of 1. F of x equals a1 times x plus a naught. And hopefully that's something familiar. We have f of x equals 5x minus 7. That's a linear. Then a degree of 2 gives me a quadratic, and that is f of x times a2, x to the power of 2. That's my degree. So example of that is f of x equals 2x squared plus x minus 9. And then we have a couple more examples. A degree of 3 means cubic. And so my highest degree here you would see would be 3. And then an example here, f of x equals 3x cubed plus x squared plus 3x. And then finally, quartic, which we won't see too much of this, f of x equals a4 times x to the power of 4, and that's our highest degree. And then an example would be something like f of x equals x to the power of 4 plus 2x minus 1. And what I really want you to notice again is that we always arrange the terms in descending order from a left to right. So for this last example here, we have x to the power of 4 plus 2 times x to the power of 1 minus 1. We would not put the 2x in front of the x to the power of 4 term because we want to make sure that we are in descending order of degrees. So let's see some of the practice. So we give you an example, determine whether each function is a polynomial function, and if so, write it in standard form and state its degree. So remember a couple of the definitions of what it would be to be polynomial. So we have to have a exponent that is a whole number. That is the most important. So f of x is equal to 2 times x to the power of 3 plus 5x plus 8. This is a polynomial. We don't have any other special exponents here, so this is a yes. And then the highest degree usually comes in the first term. So that is 3. If you go to the chart above, you'll see that a degree of 3 is cubic. And then in standard form, we just want to make sure that we have the terms in descending order of degree. So it seems like it is already in standard form. We just want to make sure we write it properly. F of x is equal to 2 times x to the power of 3 plus 5x plus 8. So let's take a look at the function of g of x. G of x equals negative 0.8 times x to the power of 3 plus the square root of 2 times x to the power of 4 minus 12. So again, a polynomial just depends on making sure that these exponents are whole numbers. Right? So yes, this is also a polynomial. And I've pointed out the two exponents, and the degree of the polynomial is the highest exponent. So in this case, it's 4. And from the chart above, a degree of 4 is what we call quartic. And here, g of x seems a little bit out of order. It's not written in standard form unless it's in descending order of degree. So here we'll have the square root of 2 times x to the power of 4 minus 0.8 times x to the power of 3 minus 12. So let's take a look at h of x. What you want to notice here is, again, if you're taking a look at the exponents, are they whole numbers, positive whole numbers? This one is 2. This one is a little different. This is negative 1. So that negative 1 automatically tells us that this is not a polynomial. So this is no. And then we don't have to fill in the rest of the chart. If we look at k of x, again, we look at the exponents, positive whole numbers. Well, no, there's a problem here that's unfamiliar, and that has an exponent of x. So this is also not an example of a polynomial. All right, moving on. So evaluating a polynomial function, taking a look at an example, let's say we have the polynomial function of f of x is equal to 2 times x to the power of 4 minus 8 times x to the power of 2 plus 5x minus 7. And we want to evaluate that function when x is equal to 3. So my first step is to write the original equation. My second step, which is really important, we substitute 3 for all the x values. And then I want to make sure you use brackets. When we're dealing with positive numbers, sometimes it's not as important, but definitely if we need to substitute a negative value, we want to make sure we use brackets. So we substitute all the x values with the value that's given for x, which is 3, and then we simplify. Remember, when we evaluate powers and multiply, we want to make sure we're using our order of operations, BEDMAS, which means we do brackets, then exponents, division, multiplication, addition, and then subtraction. So what I did here was simplify each of the terms using order of operations, and I got 162 minus 72 plus 15 minus 7, and our polynomial is equal to 98 when x is equal to 3. So let's go ahead and talk about the end behavior of a polynomial function. The end behavior describes how the ends of a polynomial behave as x approaches positive infinity, and that's as x gets bigger to the right, and negative infinity as x gets smaller to the left, and it depends on the leading coefficient of the function as well as the degree of the function. So we're talking about if I have a quick graph here of a parabola, the end behavior describes what is the parabola doing as it moves towards positive. This is positive. And what is the parabola doing as we move toward the negative side? All right, we can have different polynomial functions. Some might be something totally different like this, in which case we can see there's a difference in the behavior or which way the polynomial graph moves as we go towards the positive side and as we go towards the negative side. So let's get a better description here. So the sign of the leading coefficient determines the end behavior on the right side. So be sure the polynomial is written in standard form so the leading coefficient is easily determined. So if the leading coefficient is, let's cross this out, this should say positive. Sorry about that. The graph goes up to the right. So positive means it goes up to the right. If it's negative, then the graph goes down to the right. Now, the degree of the polynomial determines the end behavior on the left side of the graph. And if the degree is even, then both ends go the same way. So if the right side is going up, then the left side will go up. The right side is going down, then the left side will go down. And that is if the degree is even. However, if the degree of the polynomial is odd, the ends go the opposite way. So if my right side is going up, my left side is going to go down, and vice versa. So an example of how we would describe this, for a polynomial in standard form, that is negative 0.5 times x to the power 4 plus 2.5 times x to the power of 2 plus x minus 1. We make sure it's in standard form. The leading coefficient is negative, right? The leading coefficient here is negative 0.5. It doesn't really matter that it's 0.5, but it matters that it's negative. And so since it's negative, this describes the end behavior on the right side of your graph. So as you're going towards the right, the graph is coming down. The degree of the polynomial is 4. That's the exponent. And that's even, so the end behavior on the left is the same as on the right side. And actually, this should be a negative. Well, what if our polynomial is in factored form? So we have g of x is equal to 2 times bracket x minus 1 bracket x plus 3 squared. The leading coefficient is positive, right? It's 2, so it's positive. So the end behavior on the right side is going to go up, the positive side. The degree is the sum of the exponents, which in this case is actually 3, because this first bracket has an exponent of 1, and then the second bracket has an exponent of 2, and so we have to combine those two exponents. So it's actually 3, and it's odd. So the end behavior on the opposite side, on the left side, has to be opposite what it is on the right side. So let's take a look at graphing this function. F of x is equal to negative x cubed plus x squared minus 3x, plus 3x minus 3. So I want you to start by filling in the graph. Start with the table of values. So we've talked a little bit about Desmos, and that's an online graphing tool. There is a tutorial that's in our classroom resources, so you can watch that. But we want to use Desmos to complete the graph. If you would like to, you can also go ahead and graph it on paper, but somewhat it's easier just to do it on Desmos. So here's our table of values for our function, and we can see that we have 1, 2, 3, 4, 5 different points to graph. So in Desmos, you would use the plus button, add a table, input the values from the table above. Okay, again, there's a tutorial here, but I'm going to go over the description. Once the values are in, use the regression function that matches the degree of the polynomial. So since the highest degree of the polynomial is 3, it's cubic. So you're going to look for cubic regression and click on each of the points on the graph so the coordinates are shown. This results in the following graph on Desmos, and you should try it on your own and make sure it comes out just the same, okay? So we went to the add button, a drop-down menu comes up, and you can enter a table of values. So then I entered all the values from the table that we have above. And then down here, I can click on, this is a drop-down menu, and you want to pick cubic regression, and that is because the degree on the function is 3. So what'll that do? That'll have all your points plotted, and it will also have the function going through it. So let's talk about the end behavior. If we recall, the sign on the leading coefficient, I'm going to scroll back up, the leading coefficient was negative. Since it's negative, that means on the right side, the end behavior should be going down. And if we take a look, yes, we're going down. Now the degree of the polynomial is 3. 3 is odd, and so that means on the left side, it'll be doing opposite what it's doing on the right, which it is. So I just want to take a table, graph it on Desmos, and confirm the end behavior based on the leading coefficient and the degree of the function. So try that on your own on Desmos. Make sure you get something that looks like what I have entered into our document. Okay, let's move on. So here is where I want you to do this new graph. So once you get a hang of it and you practice from the first example, you can try this one on your own. And let's just double check what should be happening. And then when you get your graph, you can confirm that that is what's actually happening. So here, my leading coefficient is 1. It's positive. So on the right side, as x approaches positive infinity, then it should be going up. So y should be approaching positive infinity. And that's because it's even. Now the highest degree is 4, and that's even. So that means as x approaches negative infinity, where it goes towards the left, it's even. So the end behavior is going to also be the same. All right, so that is what you're going to check once you have all of these values in. So let's just go through a couple of examples of how you're going to evaluate this. Remember, to evaluate a function, we substitute values, and I have them all given: -2, -1, 0, 1, and 2. And so we are going to first evaluate the function at -2. In which case we use our brackets, and we'll have -2 to the power of 4 minus -2 to the power of 3 minus 4 times -2 squared plus 4. Simplifying a little bit, we'll have 16 minus -8 minus 4 times 4 plus 4. And then we have 16 plus 8 minus a negative number, minus 16 plus 4. 16s cancel here. We have 8 plus 4, which is 12. And that's what goes in here. We'll do another one, and then I'll let you go ahead and finish the rest. So f of negative 1 is going to be a negative 1 to the power of 4 minus negative 1 to the power of 3 minus 4 times negative 1 squared plus 4. Ones are a little more easy to simplify. So this is 1 minus negative 1 cubed is going to give me negative 1. And then negative 1 squared times negative 4 is going to give me negative 4 plus 4. And what we end up here is 1 minus a negative, which is 1 plus 1. And we end up with 2. So go ahead and do the substitution for the last 3 values. So you want to evaluate f at 0, you want to evaluate f at 1, and you want to evaluate f at 2. Once you have that in your table of values, go ahead and go back to Desmos, fill in your table, do the corresponding regression. The highest degree here is 4. So when you're looking to do the corresponding regression, you should be looking to do quartic. Remember the name of that? And then you should be able to get the right function. Then you want to confirm the end behavior, which we did right at the top. And if there's any problems, let me know. But once you have your graph on Desmos or by hand, it's up to you. I want you to either take a picture or screenshot and then upload it right here into the document. Here's another one that you're going to do. F of x equals x to the power 4 minus x cubed minus 3 times x squared minus 2. Again, work that out on Desmos. And finally, a third one to do. Okay. All right, so those last couple of functions will be your independent practice. And then we're going to go on and just talk about the end behavior in this chart. So given the following functions, determine if the leading coefficient is positive or negative, and if the degree is odd or even, and then describe the end behavior of each function. So I'm just going to do a couple of them with you and then let you go ahead and do the others on your own. So leading coefficient here is 2. It's positive. The degree, again, remember when we don't have anything shown, it's really a 1. And so 1 plus 2, which is the degree on the second bracket, that's really a degree of 3, which is odd. So a positive leading coefficient means that as x approaches positive infinity, y also approaches positive infinity. It's going up to the right. An odd degree means that on the left side, as x is approaching negative infinity, as we move to the left, then y is going to be opposite. So it's going to approach negative infinity. It's going to be opposite the right side. Taking a look at the next example, we have a leading coefficient of negative 5. So it is negative. Again, we have a degree here of 3, but then we have another bracket, and we assume that it's a degree of 1. And so 3 plus 1 gives me 4, and that's even. So since my leading coefficient is negative, as x moves to the positive, to the right side, y is going to move to the negative. And then since my degree is even, as x moves to the left side, the behavior is going to be the same. All right. Actually, go ahead and try to do the last ones on your own. Try to take a look at the leading coefficient and then the highest degree and describe what the end behavior is. All right? All right. I will see you next time. Thanks.